All right, welcome to the session types functional pearls session of ICFP 2023. Today we're going to be hearing two functional pearls, which are always very nice papers to get to read and to get to hear about on the stage. So we're going to start with Peter telling us about building intrinsically typed sessions using callbacks.
Well, thank you, Andrew, for the introduction. I want to tell you about a discovery that I made earlier in this year about session types. So a very quick recap. A session type is really a type that describes a communication channel. In the simplest form, essentially, it describes a sequence and the direction of messages. So the S down here is a typical syntax that's used. So a session type may either be you want to send some T and continue with S, or you want to receive some value of type T, continue with S, or end means you've got to close the session. And at the bottom you see some examples here. Like here, this would be a server for a unary function. It first receives an integer argument, and then it sends out the integer response, and then it closes the connection. And another concept that's often used, I'm not sure I'm going to get to this in the talk, that's the dual, so the type of the client on the other side, that would be, you would get that by just reversing the direction of the communication. Yeah? So the client has to receive an integer, send an integer, and then receive the response, and then both agree to close the connection. A typical API for session types transforms the types of channel ends. So for sending, you take the value that you want to send, and it's paired with a channel that is ready to send something, and then continue as S. And then the act of sending turns that pair into just the continuation session, like the rest of the communication channel, which runs the rest of the protocol. Similarly, receiving on a channel that's ready to receive returns the value received and the channel where you can do the rest of the communication. And in this case, close, so there are different ways of doing that, but here I'm just saying close consumes the channel entirely and returning something, in this case a unit value. As you may have gleaned from the connectives that I'm using, session types are linear, and here I've brought you a little piece of code for such a unary function server. And here you can see initially the channel of type C0, it starts at this unary function, unary whatever protocol. Then after receiving the argument, the remaining channel is typed at, send an integer and then end. And then after sending, the only thing that is left to do on that channel is you can just close it. And that's what the code essentially does. And it's crucial that session types are linear, because otherwise, if I were able to use the C0 value several times, then I would just break the protocol. So after I've done the first receive, then, I have to send something on the channel, and I can't receive something again because the client would expect something different here. So what am I going to show you in this paper? Well, actually, a brief glimpse in this talk. It's actually possible to come up with a safe session type API without using any of that linear type stuff. And this linear type stuff has hindered adoption of session typing because most host languages, until the advent of Rust, I guess, didn't have any notion of linear types, and linear Haskell, I have to say, didn't have any kind of linear types, and so you were always a little bit at odds. So you have this nice theory where everything is protocol safe and type safe, and then there's always this linearity. Do I actually adhere to that? Okay, so here I'm telling you, you can do it, and you can be type safe, protocols safe without using any kind of linear types. And it turns out a modicum of index types, or you might say GADTs, is sufficient to do that. And the secret sauce to do that is something that any functional programmer should know and love, namely callbacks. First-class functions, the heart of functional programming, and you store them in a data structure. So exactly like the first ideas of functional programming. Right. So how do we come there? Well, we steal, right? As usual. So some very clever guys here, Mew, Ferreira, Yoshida, and Zhu. Actually, that's already 2 years old. They came up with this idea of embedding multi-party session types, which is way more complex than we are going to discuss today, into TypeScript. And they developed a type-safe TypeScript embedding of session types, which didn't require linearity because they, well, here you can, maybe it's probably too small to read. Yeah, so it provides developers with TypeScript APIs generated from a communication protocol, and this generated API complements the event-driven style of programming that you have in web programming. And we'll come, yeah, so this is too small. And what exactly did they propose in that paper? They said, we want to use a callback style API for clients and servers. What you do every time when you have a JavaScript or a TypeScript API, almost all of them are like that. So our toolchain produces TypeScript APIs in a callback style to statically guarantee channel linearity. And when I read this, I thought, wow, TypeScript doesn't have linear types, and somehow they do that. So how do they do that? Well, so they translate their protocol into endpoint finite state machines, and then in their callback API styles, the type signatures of callbacks are generated for transitions in these finite state machines. And now I don't expect you to read the rest and that, just have a look. So this is what their generated stuff looks like. And you see the type with the telling name S40 and the interface S38, message S38, underline query, blah, blah, blah. And these types show up, albeit sparingly, in the code that you have to write. So that may be a bit confusing. And the question arises, well, it arose for me, can't we do that better somehow? So what would the callback style look like if we were using a functional language in a more serious way? And it turns out you can do that, and there is no code generation required whatsoever, which means there are no interfaces, there are no funny generated names in interfaces that you may have to remember, or that your typing environment has to remember. Instead, what we're going to do is we're going to do a similar route than monads or even free monads. We're going to have a data structure command, and this command data structure will be the container for a lot of callbacks. And then what we have to do is we just have to interpret this data structure. While I believe I could pull this off in Haskell, when I was writing the paper, I was too tired to do that, so I used Agda as the implementation language. I thought I would get more quick trajectory, but anyway. So here's the same program that you saw a couple of slides back with the linear style in this command style. And essentially what we do is, well, this is the specification of the negation server, and it's a command with the session type of a unary function, more or less. And it says receive something, and that's the callback for receiving, send something, that's the callback for sending, and then close. All right, and here we can actually, what the callbacks have to do, we can look up in the paper by Mew and others. So they say for callbacks, sending actions correspond to callbacks prompting the payload type as a return type, so that the return value can be sent to the runtime, by the runtime. The receiving actions correspond to callbacks taking the payload type as an argument, so that the runtime invokes the callback with the received value. And I'll show you in a couple of minutes how that, well, actually in a minute, what that looks like here. Well, here, let me just give you a brief one here. Receive, well, we expect the value of the payload type to come in, so that value gets bound to X. A here, the A value is the application state. We somehow need to put that. And that's the new application state, the outcoming application state. Similarly, for sending, we obtain the application state, and we need to output the value. I mean, somehow we need to extract the value that we want to send from the application state. So that's what the callback and send is doing. In the TypeScript implementation, being a little bit imperative, the application state is implicit, so you don't have these extra arguments and return values flying around. They're just encapsulated in the generated library code. All right. How do we encode session types? So that shouldn't be much of a surprise. So we're more or less translating these grammars into ACTA. I'm not sure, I don't see questioning faces, so I guess I don't need to say much about it. Let's look at the commands, right? So commands work on an application state A, as I just told you. Yeah? So the command type has to be parameterized over A. Then it takes a session type as an index. And essentially close, well, close has just the index end, and it just doesn't do anything interesting. For sending, we can see here, so this is the sentence that I stole from their paper. For send, we have a callback that elicits a value of the payload type T from the application state, and it can also transform the application state. Well, and then it takes the continuation, right? I mean, the next command. And taken together, that's the command at this type, send a T and then S. And while almost duly for receive, the receiving actions correspond to callbacks taking the payload type. Well, we're taking the payload type and transform the application state so that we can somehow integrate that into the application state. And then we take the continuation, and that gives us a command of receive a T and then S type. And then you need, well, the T's are the syntax of the payload type, so you somehow need to translate that into ACTA, but that's just an implementation detail. So one more thing that I just mentioned on a previous slide is we somehow need to execute this, right? So we build a command data structure. Now we need an interpreter for that data structure. Or you could compile it, but you're just interpreting. And as you can see, this interpreter is really, really simple. Yeah, so if you say close, you close. If it's send, well, it just extracts things from the state in the right way, and it sends. Receive is receive, so wow, that's it. But there is some proof application behind that, because that's like the only place in the whole system. Yeah, I mean, if you use it as, if you build your code on top of that, that would be your library, and I would say it's some sort of trusted computing base, and that's the only place in the system where you could break the correct linear handling of a channel. Now, because here you have this channel as an argument, and here you have to ensure that this channel is really handled linearly and nobody messes around with it, and that the commands are kind of interpreted faithfully. That's, of course, a proof obligation. Right now, this is done by inspection. I believe more could be done about that. I have some ideas, but I'm hoping that some clever person in the audience maybe comes up with a clever way of getting rid of this proof obligation. Right, and well, so that was kind of the starting point. And then I thought, okay, this has to break as soon as I put in more features of session type. Somehow, there's some place where this is going to break. Well, it turns out no. So far, the features that I checked out just work. So, for example, you have selection and choice, which is kind of branching in a protocol. So you have two operators in traditional session types. Namely, you have internal choice, where your code can choose between different continuations indexed by some label L here, or you have external choice, where your code can handle different continuations. So you receive an indication, a label that tells you this is the continuation that the other end of the channel has used. Well, and then there's the simple matter of encoding that. So we have a finite set of labels, so that should be encoded as a finite set in ACTA, and then you can more or less write down those predicates, those types. So this is one possible. Well, I should say the most convenient possible interpretation of these session type constructs into ACTA. Essentially, you model here this indexing by L by a function from this finite set into session types. Well, other encodings are possible, but they break the strict positivity of the type, so you don't really like them that much. So what do the commands look like? Well, the select and choice, if you don't look careful enough, they look extremely similar, but the difference is just a single bracket. Yeah, so for the choice that is that is interpreting the external choice, there is the first argument is a function that takes a label and delivers the command corresponding to that label, processing that particular, the chosen, externally chosen continuation. And for the selection, you do this choice by yourself, and then you just continue with the continuation that you choose. Yeah, so here you have two arguments. For the choice, you just get a function that handles the incoming label and then goes on. And well, writing code with that is, again, straightforward. And here is a nice example where you see that you can use the host language to advantage to write really modular code. Now, it gets really readable, so you can name your session types. So I've thrown in a binary protocol, unary protocol, and then you can form the arithmetic server. Well, the approximation to the arithmetic server, that's kind of a standard example, just as the external choice between the binary and the unary. Yeah, and then, so you just use the choice, and so it's really straightforward to write that code. And because the command data structure is indexed by the session type, once you have specified the session type, the programs almost write them by themselves. Yeah, because when in Acta you have this interactive way of constructing your program. So you would say, oh, this arith command, you would say it's a command of this type arithp, and you put a question mark at the point where I have the choice. Well, there's no other possibility than putting a choice there, because the type of arithp tells you this must be the choice command. So there's nothing else you can do. And once you get here, it's obvious from the protocol definition, this must be a lambda, and it just has these two cases. There's no other possibility. And here, here I could choose any command that has the suitable session type, but you can, I've shown you the necp, I didn't show you the addp, but it's not much different from that. All right. So in the interest of time, I will gloss over that a little bit. Next up is, of course, recursion. So far, we only looked at finite types. That's the first place where things get a little bit more involved. So you have a mu type and type variables. You encode them in the usual way. Let's not get too much carried away. So you get commands. You get a looping command that takes the command for the body of the loop, and then the continuation, and you have a continue, and the continue essentially works like the break statement that you may know from Java. In Java, you can also break to a particular label, and that allows you to leave a certain number, and actually an arbitrary nesting of loops. And similarly, that's how this continue works. So if you have several loops, you can jump out any nesting level of the loops as you might expect. So one thing that's interesting, maybe this loop command, as you can more or less see from the type definition, it handles all loop iterations in the same way, right? So this is the code, this is the command for the loop body, so for all iterations of the loop body. So this is probably fine for a server, but if you write client code against such a recursive type, that might be a bit annoying to do so. So fortunately, you run into this issue as soon as you try to write any sort of example. So there is an additional client command which is called unroll, and it takes a command for one iteration of the loop, and then you are back at the head of the loop, and you can then specify another command for the loop. So this means you can kind of unroll one iteration after the other with this unroll command, and thereby you can also write kind of finite client code that type checks against a recursive session type. Well, that's what I just said. So as I said, so that gets a little bit more tricky in implementing things. So the interpreter has to maintain a stack of continuation, which are essentially pending loop commands. as you can see here, and I don't have time to go into that, so there's a whole page in the paper dedicated to that. So the command stack has an interesting type, let's say, and it gives rise to some interesting complications. And then as soon as you have loops, you also run into termination, and ACTA doesn't like you to have non-terminating code. So that means the interpreter actually just runs to the first continue, and then it issues something, you could call it a resumption. So it's a continuation paired up with the current application state. And then you can kind of limit the places where you have to use pragmas to convince ACTA, this is non-terminating, to just a place, to just a small loop where you unfold this resumption and call it the interpreter again. Right, yeah. And then there are some further variations that I tried. So there, you can find them in the paper. So 7 years back, oh God, Vashko and I, we proposed something called context-free session types, where the structure of the types is, so here is traditional session types are all tail recursive. So you always have the form do something with a value of a type and then continue with S. Yeah, so send something and then S, or receive something and then S. And in context-free session types, we have a symmetric concatenation operator, so where you can compose protocols in any way. So that works as well. So you can encode that as well. The next question is, of course, what about having more than one channel? So far, I only showed you types and code that dealt with one channel. Well, that gives another level of complexity, but you can do that as well. And at that point, you get close and you run into similar issues as with multi-party session types. Yeah, so the paper gives some more information about that. So this gets a bit hairy. Another thing that you can do is, so the callback functions that we've seen, I told you, they all kind of look at the application state, they modify the application state, so it seems, and it seems quite similar to what you would do in a state monad. Yeah, so you could say, oh, there is this application state monad, and all I'm doing is feeding in stuff and pulling stuff out of this application state monad. Indeed, you can do that. You can use a monadic interface to callbacks, and probably that's the way to go, because maybe you want something, your application code wants to do something more interesting than just adding two numbers. Maybe it wants to do some I/O or something. And then you would have to have monadic callbacks. So that's also possible. It's described in the paper. There's some technical issue right now with that doesn't let you pull it through all the way, but you can see in the paper a description of that. And that makes me come to the conclusion. So I've shown you that there's that callback style enables you to safely embed session types in a language without linear types, really. If you use such a command data structure with index types, that completely avoids any code generation issues. Many styles of session types can be encoded. As I've shown you on a very small scale, it's also very nice to use modular protocols and modular implementations of protocols in the way that you saw here. Future work is, I mentioned that already before, like this proof obligations on these interpreters. I mean, all the interpreters are very similar to the one that I've shown you on that first slide. They just get more cases, but they don't get significantly more problematic. Then, of course, I would like to have the final solution for the monadic case. And with that, I can only encourage you to check out the artifact and have a look at the paper. Thank you for your attention.
Thank you very much. We have plenty of time for questions.
Hi, Simon Fowler, University of Glasgow. Thank you very much for a very nice talk. So I agree that the encoding seems very, very nice for the single channel case. So you acknowledge that it's slightly more complicated when you've got multiple channels. So I was wondering how the complexity of multi-channel compares to other AGDA encodings, for example, ones using leftover typing.
So what was the last? I didn't understand the last sentence.
Sorry. So I was just wondering how your multi-channel version compares with other implementations in AGDA, where we've got explicit linear references, more GV style, allowing multiple channels.
Okay. As far as I know, the typical style that you would do is you'd have some kind of linear state monad that encapsulates like a vector of channels. This is exactly what the interpreter does here. So the underlying implementation is probably what you also imagine. On the user level, you run into similar issues with like causality as you run in with multi-party session types. So I'm not. Probably you would want some extra layer that makes it more convenient, because otherwise you would have to kind of repeat things too many times or something like that. I don't have much practical experience with that. I mean, so you can. So with the multi-party stuff, I actually managed to get the AGDA compiler to work. It didn't work for all the artifact people. I apologize for that. But you can actually try it out and run the code with this multi-channel. And if you have a nice application, well, let me know about that.
Thanks very much.
Hello, I'm Facundo Dominguez from Twig. And I was wondering, this approach seems to give a nice solution for AGDA, but what do we do in Haskell when we also have linear types? Should we use linear types in the traditional way, or should we try something like this instead?
That's an interesting question. I don't really have a good recommendation for you, I guess. I would say that even though you have linear types in Haskell now, that doesn't obviate the use of monads for encapsulating state. So a nice thing about this approach is that you actually have your action or your command as a data type, which you can manipulate independently without caring for any linearity issues. If you need that, or if you want that extra flexibility, I would think that would be more convenient. Yeah, that's, I guess, all I can offer here.
Thank you.
Thanks for a nice talk, Peter. This is Sam Lindley, University of Edinburgh. Well, partially in answer to that question, take a look at a paper by myself and Garrett Morris. I think it was Haskell Symposium 2016 on embedding session types in Haskell. I wondered whether, given that you're doing this in AGDA, a dependently typed programming language, have you tried to encode dependent session types?
I haven't, but given that the language is, the underlying host language is dependent, it shouldn't be an issue. Yeah, that's probably easy to try out.
Thanks.
Hi, Mike Sperber, Active Group. It's probably a stupid question, but your construction looks similar to sort of the free monad pattern, right? With the exception that the command is usually returned by the continuation as opposed to. So could this pattern be generalized to fit somewhere in the hierarchy between like functors, selective functors, monads, and given laws and things like that?
Yeah, actually, when preparing the talk, I was wondering something like that. I guess in the current structure, it would be more like an applicative, because you only have, or there's this variation of applicatives, which escapes me, that by Simon Marlowe and others, where you have some finite choices inside of the applicative.
Yeah.
Selective, right?
Yeah.
Yeah. So that could be related. Yeah, but it only occurred to me in the last few days that it could be something like that.
So what
I'd certainly like to explore is in proving this interpreter correct, I was thinking, and that was also coming yesterday, the talk about choreographies, Haskell. They also use free monads for that. Yeah, so instead of having the encoding directly in the interpreter, you could kind of outsource this by interposing a free monad, and then, you still need the interpretation of the free monad, and then you would still have to have some proof obligation that this does the right thing.
Okay, thanks.
Yeah.
All right, let's maybe take a last question as they get set up with a remote talk.
Hi, Gabriel Radan in RIA France. So the original message that you wanted to bring session types to, lots of languages that don't have linear types, most of them are not pure. So do you break your guarantee when you have side effects?
Do I? So the question is, do I break purity in that?
So in Agda, you're in a pure context. But if your host language is not pure, does that break also guarantee regarding pseudo-linearity, let's call it?
I guess you could break purity in this TCB, in this interpreter, which is why there is a proof obligation. I mean, this interpreter runs on top of the I/O monad, and even in Agda, in the I/O monad, you can do whatever you like.
Yeah, I'm talking about the callbacks.
The callbacks. Well, right now they are pure, right? And what I was imagining in an extension was that you make it monadic and maybe give it access to some limited version of the I/O monad.
All right, I think
I guess it's something to discuss offline, right?
Assuming that we're ready for the next talk. Okay. Thank you again, Peter.